The first thing we have to do is figure out what these compounds are. Immediately we can identify each as being an ionic compound, because each consists of a metal and a nonmetal. The next step is to figure out what charges these ions are likely to have. Using the periodic table trends handout, we find these are likely charges. We see that there must be 2 chlorides for every 1 magnesium in order to get the charges to cancel. And there must be 2 Na to get the 2 plus charge on the sulfide to cancel. From a solubility table, we see that chlorides are almost always soluble, so this compound is going to be dissolved in a water-based solution. And sodium-based ionic compounds are always soluble. So we can also say this will be a dissolved aqueous compound. Because these compounds are dissolved and they are ionic compounds, we know they have dissociated into charged ions. So we're back with Mg2+ and 2 Cl-, and 2 sodium+, and these are all aqueous. Now for the reaction part. The cation from one compound can combine with the anion from the other compound. Because both magnesium and sulfide have 2 charges, they can come together in a 1-to-1 ratio. So we could write the compound as just MgS, but we need to know whether magnesium sulfide is soluble or not, so we can tell whether it is going to be in the aqueous phase or precipitate as a solid. When we look at the solubility chart, we see that sulfides are insoluble except for group 1 and 2. Magnesium is in group 2, so this is an exception and it is soluble. So now the actual reaction can happen, if there is one. So what we have to look at is the possibility of the cation from one compound combining with the anion from another compound. So if there is going to be a reaction here, it would be the precipitation of magnesium sulfide. So what we have to do is figure out if magnesium sulfide is soluble. We look on the solubility table and we see that sulfides are mostly insoluble except for group 1 and 2 compounds. So it is paired with a group 2A compound, so that is an exception to the insolubility of sulfides, so it is soluble. So we could write it in a 1-to-1 ratio, because a 1-to-1 ratio is fine to cancel out a 2 plus and a 2 minus. But we're talking about the net ionic equation, so we're probably not going to want to write it like that. We're going to want to show that being dissolved, these are in fact aqueous ions. And then we can look at the other possibility for the formation of a new compound in an exchange reaction, which is the anion from the first compound combining with the cation from the second compound. We know that all sodium compounds are soluble, and most compounds with chloride as the anion are soluble. So this is a very soluble compound. So we can write it ions aqueous so that is our complete ionic equation. But what really reacted here? Nothing. We just have ions mixing together. Notice that everything on the top has its counterpart on the bottom here. So every compound on the reactant side there's the same compound on the product side. So we can cancel out magnesium 2 plus, we can cancel out chloride minus, 2 of them, 2 sodiums cancel out, 2 sulfides cancel. So because no insoluble compound was formed, there is no precipitation and there is no reaction. So no net ionic equation. But if instead of magnesium we have zinc, also with a 2 plus charge, we can write zinc chloride like this. And when we consider what can happen when cations exchange with anions, the zinc could combine with the sulfide and make zinc sulfide, which is not an exception to the insolubility of sulfides. So zinc sulfide is insoluble, therefore it exists as a solid. Let me write out the whole ionic equation again. We know that when we write aqueous in front of a compound, it's saying that if it is an ionic compound, the different elements both exist as separate ions. So a better, more descriptive way to write the reactant side of this equation is like such. We saw that a product will be zinc sulfide, and then the sodiums and the chlorides will still be dissolved and ionic aqueous. The sodiums and the chlorides appear on both sides, so we can cancel the sodiums and the chlorides. And what we are left with is our net ionic equation. And I'm just going to put it all together on one line, and that's it.
Made with Doodlecast Pro.